All right, here's another example that would be in class 15, except that we don't. I don't think I'm really going to do a slider crank problem for any of the homework right here, but I did want for completeness to make these videos. So maybe in a later date, a later time, I will ask for one of these. But anyway, here's the example 6-9 out of Norton's book, where we have, again, a 40 millimeter crank, 120 millimeter connecting rod. There's an offset of negative 20 millimeters so that the line of action is actually below the pin. I think for this, we're going to know what the slider velocity is going to be. So we want to get omega 2 right here, and we don't know which direction it's necessarily going to go. And we want to get omega 3 right here. How is that rotating? We want to get the velocity at A, and we want to get the velocity at B, which doesn't make any damn sense because that's actually the thing on the inside right here. So I guess we could get the velocity of A as well, but I don't seem to have calculated that. I don't know why. Maybe something bright and shiny came around to distract me. So, but anyway, we've done, apparently done, and I'm asking for both configurations, but I'm not going to do both configurations. Let's only do the main configuration here. So that should be the 95 right here. And so that's, let's do the first configuration, not the other configuration right here. So ignore that. And so what we would end up finding here is that we have, we would use the equation omega 2 is equal to d dot times the cosine of theta 3 divided by a cosine of theta 2 times sine of theta 3, and then minus sine theta 2, times cosine of theta 3. And what we end up finding is we get 1200, right? And because it says the thing is giving, I'm going to assume that must mean that's going to be going in that direction. All right, that's what VB is, and that's going to be the cosine of 150.11 divided by 40 times the cosine of 95.8 times the sine of 150.11 minus the sine of 95.80 times the cosine of 150.11. And what we end up finding is we get negative 32.02 radians per second. So that's obviously, that means that that's going to be clockwise. So I have drawn it wrong up above. So it's actually going out that way, which kind of makes sense that it would. I'm going to guess that this one is actually going to be counterclockwise, this omega 3. Because this thing is starting to get squatty, but actually we don't actually know. That's not necessarily true because it could be rotating. It could be rotating. Yeah, no. Okay, I can see it's probably rotating that way right there, right? I don't know. Let's see what happens. We get omega 3 is going to be equal to A times omega 2. So we needed to get omega 2 first, times the cosine of 2 divided by B cosine of theta 3. So that's not too long of an equation. So we get 40 times our negative 32.02 times the cosine of 95.80 and divided by 120 and the cosine of 150.11. And what we end up with is a negative 1.2 4, 4. So I guessed wrong up above. It is actually going to be a clockwise rotation right here, which I guess kind of makes sense. At some point, there's going to the connecting rod is going to change its direction of rotation, right? It's going to, at one point, it's going to be like so. So this guy is coming upwards. Now, what we could have done, by the way, and I should have done this in the other problem, is to draw out the velocity of this, right? So if that's the velocity here, oh, this is going to be interesting right here. So this is going to get, everything I've drawn right here is going to be in the way. But we want to draw a line that's perpendicular to this right here. And we would draw a line that's perpendicular to this. Okay, so looking at that, you can see that way the hell down here somewhere is going to be the instantaneous center of rotation. And so that we're going to find that the velocity, the angular velocity is going to be over in that direction, so that we can achieve that and that. That means so about that ICR down somewhere down there. But that ICR is describing this thing, and this omega 3 right here, right? That's the omega 3 is rotating about that ICR down below. And so you can see that it's a really small value. So in order to achieve these velocities right here, it had to be a really long lengths of those relative that RB with respect to ICR and RA with respect to ICR. We're really, really far down. It's understandable because this right here is close to being 90 degrees. If it was 90 degrees, this connecting rod would be in pure translation, right, to the right. And then once it got to that point, omega 3 would probably reverse direction. And that would kind of make sense, right? Because if it was in this orientation right here, where it's moving to the right and it's rotating here, this guy would definitely be rotating down when it got to that position. But right now, and its orientation right here, it's moving like right there, right? So it's moving there, and so as this thing is moving along right there, this thing too is rotating that way. So it changes direction when it gets up to that 90 degrees position. And I just want to open up Norton and check out this example problem, 6-9. Which you should be doing too, right? You should be looking at following along to these things. And my video here is not to replace what's in Norton, but to actually try to facilitate it, make it a little bit easier to follow along. It says example 6-9, but I don't see an example 6-9 in here. Where the hell is 6-9? There you are, right there. And okay, so they don't actually do the velocity. That's interesting to me. They don't actually find the velocity in the example. So that's probably why I didn't do it. But let's go back and take a look at where this stuff came from. Remember, this was the same vector, the same the same vector loop as the crank slider. This is the slider crank, and so you ended up with an A omega 2 J e to the J theta 2 and then minus B omega 3 J e to the J theta 3, and then minus a D dot, right? So in this case, D dot was the input, right? It was the thing that we were given. So what we have here is this guy is going to be VA, and then this guy is going to be B, remember it was A with respect to B in this case, A with respect to B, and this was supposed to be VB, and remember that the reason why this one was a minus in this case is because they chose the vector loop back in up here. They chose this arrow downwards right there, right? So so that ended up making we ended up going the opposite direction of this arrow when we went in the when we went to calculate that vector loop. So when we take the derivative of it, we're left with a negative sign right up in here. So if we wanted to calculate VA, if that was the thing that we wanted to get as part of that, we would simply multiply omega 2 right here times, yeah. So why don't we do that? So that's the only thing that we're really missing, or the only thing that's probably of any interest to us, is VA is equal to A omega 2 J E J theta 2. So that's going to be, what do we say for this problem right here, is going to be 40. And then this is going to end up being a negative 32.02 right here. And this is, remember, we're going to do here, we're going to negative sign of theta 2, which we were given, right? No, we found from a position analysis that was done previously. And then we're going to have plus J cosine of our 95.80, and if we do that, we end up with equals 40. Whoops, turn the calculator on. 40. It's getting dark in here. 32.02, and that's negative times that, and we have 95.80. And take the sign of that, and but it's negative, so it's multiply right there. So we end up with a negative, which is positive. So we get 1,274. And then we don't know if this is positive or negative. I think it's actually going to be negative. So I think it's actually going to be positive. So we go. Actually, I could probably look at the diagram and tell by that. 32.2, and I already did that. 32.02, and we multiply that, and we end up by 95.8, and take the cosine, and sure enough, that's negative, but it's a very small number. So this is going to be plus J and 129.4 millimeters per second, and we take the sum of the squares of those. We didn't actually have to take the sum of the squares. We could just actually multiply those two things by each other, but I'll do it anyway. Right here, boom, and boom, add them together, square root, and we get 1,281 millimeters per second. And we know that it's going to be in the upper right quadrant, so, and it's going to be 129.4 and 1274, and divided inverse tangent, and we get that's just going to be 5.800 degrees. And we knew that it was going to be a small number because we had 95 going on right here, so we just knew that it was going to be 90 minus that number right there. And then of course we already know what VB was going to be equal to. That is the 1200 right here, so it's just 1200 millimeters per second. That's going to the right. So if we wanted V A with respect to B, we could just subtract that thing out right there. So all we would do is subtract out B from A. So all you're left with is like 274 plus J. Yeah, we're subtracting B out, so it's 129.4 millimeters per second. So that would equal the 274 squared and 129.4 squared and plus, and then we end up with 303 millimeters per second. And this 2 is going to be in the upper right quadrant right here, so that's going to be upwards like that right there, and it's going to be 129.4 divided by 274, and take the inverse tangent of the thing, and we're left with a 25.28 degrees right there, going upwards. So if you were to take a look at that, you could kind of see which way that thing is going to go. Is going to be like upwards somewhere, like not that far upwards, but it will be upwards onto there. So that's the bottom line for this one. It's not an exciting one to do, and I don't think I actually need to do an Excel of this. Because you could probably, because we're basically, we're going to go backwards with the thing. So I don't think this serves any purpose in making an Excel for this. So I'm going to end the show here, and we'll discard this. And let's talk about one of the best guitars that I own. Right here. So first off, let me flip this thing around. Detach that. I keep hitting that as I detach it. One of these days I'm going to break it. Okay, so we've broken this thing around right here, and I'll go to camera. Okay, so we have an app for camera, and there I am right there. We got front facing. And one of the best guitars that I own, and I'm not sure he's in tune, is this Taylor. And I've owned him for a while, and I decided at some point that I wanted to get rid of the pickguard, so I got the instructions, and we took the pickguard off. Now I call it a tan line on here. But this is a Taylor. Let's actually get I put the little clip-on tuner there. It's a Taylor 814 CE. And what I did is I bought a lot of electric guitars and a lot of acoustic guitars. Well, a lot of electric guitars. And I had a couple acoustic guitars. Not very good ones. So I wanted to go I wanted to get just the acoustic guitar, right? I wanted to get one that was going to be the one that I wanted for the rest of my life, and then not to have to buy another. Just so you know, I bought some more since then. But, so I just played every single acoustic guitar that I could find. And I didn't even look at the price tag. Just wanted to find one that just like went, yes, that's the guitar. So I've had this for like 20 years now. And actually, let's see, what year does it say that it is? Does it say the year? You would think it does. Yeah, it's been 20 years. It's built in 2000. And I have sent it back to the tailor to get refurbished before.